Hello, everyone. My name is Oliver Lasnick, and today I'm going to talk very briefly about a project in my lab at the University of Connecticut that involves mapping the relationship between development and functional connectivity in the brain and how it intersects with reading disorder. So, very briefly, I want to start off with this very basic question. So, what is a growth chart? And very broadly, the way that we think of it is as this graph that shows you how certain traits, such as height and weight, change across development, and how this trajectory might differ depending on some other factor. But what about more complex traits, such as neurobiological signals? And there's some work that has been done on this in the past because these things are known to change functionally and systematically with development as the brain grows. And there's also great individual variability and perhaps even population level variability on the basis of diagnostic categories, for instance, in neuropsychiatric and neurodevelopmental disorders that warrants further investigation. So for this project, the goal was to extend this concept of age-based growth charts to functional neurobiological measures, more specifically functional connectivity, or FC, to investigate how these measures might differ between typically developing populations and those with a particular disorder. And specifically, the disorder we are interested in here is decoding-based reading disorder, or RD. And the first step was to decide from which regions of the brain we are extracting FC measures, which in this case are the correlations in blood oxygen level dependent or bold signal activity between a given pair of regions of interest, or ROIs. So because we are interested in having a model that links age to FC, as well as looking at systematic differences between controls and the RD population, this led to us selecting two sets of ROIs to use for two separate models. For both sets, the ROIs were all required to be present in this set of coordinates we derived from a literature search of meta-analyses that looked specifically for regions linked to reading, language, or RD specifically. Now, the first set of ROIs was for the distributed brain model, and it consists of 78 ROIs that only had to have come up more than once across the full set of meta-analyses, so we used fairly liberal criteria. And now the set of pairwise features it generated was very large. Recall that one feature is the connection between two unique ROIs. So when you have 78, it scales quite badly. So because of this, we did a principal component analysis on the full set of features to reduce the dimensionality of our data. And the second set was for what we termed the specific model. It had only 27 ROIs. So the set of features that it generated was actually quite manageable, only 351. So there was no PCA conducted on this set. We then constructed two machine learning models for both feature sets, trained on FC data to predict chronological age. This is what's called support vector regression rather than classification, because we are training these models to predict a continuous feature, in this case age, rather than classes. And the full set of participants, these models were trained on could either be RDs, who had scaled scores from the test of word reading efficiency or tower that fell below 85, or TDs, whose scores were above 90. All data was resting state fMRI data collected during an audiovisual movie watching paradigm from 742 children and adolescents, and it came from the publicly available Child Mind Institute Healthy Brain Network dataset. The model also used a linear kernel, and it was trained via 5-fold cross-validation and grid search in order to select the optimal hyperparameters for the model. It was also trained on data from participants across the reading ability spectrum, not just typical readers. Hypotheses were as follows. 1, functional connectivity would predict age, so there would be a positive relationship between model predictions and actual age. 2, the distributed brain model would be a better predictor of age compared to the specific model. And 3, when looking at predictions for RD and TDs for both models, we will see a gap or intercept bias between the two such that the RD group has its age underestimated. And this gap will be larger in the specific model because developmental delays in this group should be concentrated in the reading and language areas of the brain. Results confirmed that true age accounted for 8 to 16% of the variance in the age predictions for both models. This confirms that both models learned to predict age from FC data, even if they aren't perfectly precise. We also see that the model trained on more widely distributed ROIs performed better than the one trained on a reading language network ROIs, with true age accounting for twice the amount of variance in the distributed model compared to the specific. However, in terms of slope bias, the difference between the two was not significant, so the interaction effect of true age and model type did not reach significance. We then saw that with paired t-tests comparing the actual versus predicted ages for both models, the specific model actually did not show a significant difference between real and predicted age for RDs and TDs, while the distributed model significantly underestimated the age of RDs, but not TDs. However, looking at regression models which controlled for true age, we saw that for both models, the individual effect of group or RD status was not significant, nor was there an interaction between RD status and age, suggesting that RD status on its own does not uniquely account for any significant aspect of model prediction. Therefore, while we can see that there is a small group bias here, it is not significant once controlling for true age. Now, next steps are to examine features that contribute to the performance of the distributed model and to compare these to the reading and language network ROIs we identified with literature search, as well as to aging literature more broadly. When we extract the top 5% of connections that contributed to performance, we see predominantly left intrahemisphere and interhemispheric connections. And then examining the individual ROIs that turned up most often within these significant connections, we see a map reflecting the involvement of bilateral prefrontal, left occipital, and temporoparieto-occipital areas. The hope is to determine which connections and regions are driving maturational distinctions without needing to be highly selective in terms of which areas we're looking at for analysis, because we have this model whose weighted coefficients we can interrogate. So this is an avenue for future analysis that we would like to investigate more thoroughly. And in particular, I and my team are very interested to hear from people who have done research in this vein about their approaches to systematically determining what neurobiological information is highly relevant in model behavior. And with that said, thank you very much for listening. I hope you enjoy the rest of the conference, and I look forward to answering any questions you may have, as well as getting any feedback about the analyses conducted for this project. Thank you very much for your time, and also a huge thank you to all of my colleagues for our combined efforts and support.